Okay, let's talk a little bit about real-time neural materials. This is a project that we presented at SIGGRAPH last year, and the point of this section is not so much explaining all the technical details of that work, because the paper presentation from last year is a much better place for that, and instead I want to use this more as a practical example to show what the process looks like to bring a neural shading project from the initial idea to something that actually works in practice. I'll stress here that this was the work of many people, and that includes many of the slides in this section, and I'm just up here talking about it. Now, the motivation for this project was that we wanted to render really sophisticated and highly detailed materials in real time. And here are some examples of photos of real materials that we used as inspiration. We then asked a few skilled artists to reproduce some of the materials from the reference photos in as much detail as possible. These are materials that we can render today, just not in real time. And that's because they're sort of deeply layered materials that involve fairly complicated shadographs, and these are just too expensive to feasibly run in real time. And we don't have a good way of simplifying these graphs to turn them into a smaller model that runs faster but is sort of as close as possible to the original artist-created reference. So we then asked ourselves, well, what if we used a neural network to do this job, to compress this material into a sort of fixed cost block, a fixed cost network that retains as much of the complexity of the original material? Well, as a starting point, we started with the simplest idea first, which is to sort of feed in the light and the viewing direction into a small MLP with a few layers and ask it to learn the BRDF for this pair of directions. Now, we want the material to have some spatial variation, so we also learn a texture of latent codes that we also feed as input to the network. And then we train it for random directions and UV coordinates over the whole material and ask it to match the reference. So this is very simple, but when we go and try this, this does actually work. And we get a material that's a pretty close fit to the reference material created by the artist, as long as the resolution of the latent texture isn't too big. When we increase the texture resolution of the latent texture to match the source textures, to get rid of these blocky artifacts, unfortunately, the training stops working. And the reason for this is that we're now splitting our training samples over many more texels, leading to much noisier gradients and much slower convergence. And you can see this when you look at the latent texture that it learns, which sort of looks very noisy and low contrast because the training has stalled. Because we want to scale to very high texture resolutions, we need to do a little bit better than individually learning the latent codes at each of the texels. And the solution that we came up with was to replace the latent texture with a second network that we call the encoder. And this gets the stack of textures of the original material, the artist-created material, as input. And instead of learning an independent latent code per texel, we instead learn a single encoder network that learns to translate the textures of the original material into the latent texture. This has much fewer degrees of freedom. There's much fewer network weights in the encoder than there are parameters in the latent texture. And so this converges to a good result regardless of the texture resolution. And you can see this in the latent texture that it learns as well. Now, it sounds expensive to add a second big network to our material, but the cool thing is that we only need this encoder during training. After the training is complete, we can just use the encoder network to bake the encoding, that is to translate the original textures into a baked latent texture, and you only need to ship the decoder network and the texture at runtime. And so this runs at the same cost as the first naive solution, but it trains much better. When we look at the quality of the material that it learns now, we can see that it does capture the overall character of the reference material, but there's still quite a few differences, and it seems to struggle the most when the original material uses heavy normal mapping. Now, normal mapping isn't very difficult, but we're sort of wasting the limited weights of our small network to relearn how to construct and transform the input directions into sort of a local shading frame. And we can help it along by just, infusing our knowledge of how to do shading frame transforms into a fixed function component of the network. And to do this, we add a very small trainable layer that extracts normals and tangents from the latent code. And then we have a small piece of shader code that takes those directions, makes them orthogonal, normalizes them, and then rotates the view and light directions into the resulting shading frame. And that alleviates the network having to learn these sort of complex nonlinear operations. And if you do this, you sort of use the limited capacity of the network to just focus on the appearance of the material instead of relearning how to do normal mapping. And compared to where we started, this brings the quality of the network actually pretty close to the reference, without needing to add, lots more parameters to the network. And this really is the core of real-time neural materials. What I described wasn't hugely complicated, and in fact, you could probably implement something pretty close just with the tools you learned in this course. But the end result is fairly effective. The system can learn these fairly challenging artist-offered materials, but runs at a speed that's comparable to a classic Disney BRDF on modern hardware, while being much more effective at matching the reference. Besides the performance, there's a few other nice things you get with it. Once your models are trainable, you can do some things that are fairly challenging to do if you started with just shader code or shader graphs alone. The first is that you now get a dial that lets you trade off the quality of the material versus the cost by changing the size of the network. This way you can smoothly adjust the cost of the material at runtime versus its quality, but because it's trained, it preserves sort of as much of the character of the material that it can fit into the given compute budget. This kind of material simplification is really useful for scaling out across different hardware capability and, for example, for doing LOD for things that are far away or are seen in indirect bounces, but it's actually quite tricky to do when you're starting from just raw shader code. Another nice feature is that you can easily tack on additional learned components to this network if you wanted to solve additional tasks. One example in neural materials is that we added a learned importance sampling component so that we simultaneously learn how to render the material and also how to importance sample it for path tracing using the same latent texture. Another example that we added is learned filtering of the neural material. If you take the raw neural material and render it from afar, then as you would expect from a high-resolution thing, it will look aliased and noisy as you zoom out. And what we'd really like is something like the reference on the right that's rendered with supersampling, sort of with many samples per pixel. And the fix is actually very similar to what we saw at the beginning of the course, where we train a map of latent textures to minimize the error of the neural material at each MIP compared to the supersampled reference. Now, the point that I'm trying to drive home with this section is, not so much an advertisement for neural materials, but really a demonstration of what developing a neural shading application looks like and the kind of benefits that you get once you go down that route. You saw many of the same themes from the beginning of the course, where some problems that are pretty challenging to do with classic shaders, like material simplification or filtering, become a lot easier once your shaders are trainable. On the flip side, you need to learn new debugging skills for neural shading to figure out how to make them perform at the level that you need. So here, once again, you saw an example of sort of infusing something that you already know how to do into a sort of fixed function component of the network to save its capacity for the rest of the task. This doesn't work every time, but in our experience, it is a useful thing to try. What I didn't show is the many dozens of ideas that we tried and didn't work, and engineering pain that was involved in implementing and testing each one. Projects like these are what in part motivate building Slang's ecosystem, to remove the effort and time spent writing the boilerplate code that you normally need to run your shaders. I think this is a crucial piece of the workflow of developing neural shaders, and I really recommend that you try it out.